In example 3, we're given a table of data that tells us about the number of school enrollments in thousands and the number of people living under the poverty level in thousands in different regions. And we want to use this information to complete the following results. Before we get into that process, which will be similar to what we've done in the previous questions, we want to take a moment to focus on this language about the data being presented in thousands. We do this sometimes to condense numbers, just to make them smaller. But what we want to recognize is that if this is telling us the school enrollments in thousands, what we need to do to each of these values is multiply them by 1,000 to know what the actual original value was. So 20.2 in this case represents 20,200 school enrollments. 21.2 represents 21,200 school enrollments, and so on. And it's the same for number of people living under the poverty level. Each of these values would get multiplied by 1,000. So 9.5 represents 9,500 people living below the poverty level. 10.3 represents 10,300 people living below the poverty level. When we enter the data into Desmos, we're going to keep it the way it was presented. But when we get to our interpretation, we need to make sure we make these adjustments to the values, because it wouldn't make sense to reflect 20.2 people enrolled in school. We need to convert that to the 20,200 so that we're communicating information in a way that makes sense. So we're going to repeat the process we've seen in the previous examples, where we create our linear model, look at that correlation coefficient, and then use our model to predict a future or unknown value. I've already entered this data into Desmos again, so we can zoom fit to see our data better and add that linear model. We have our linear model and we have a correlation coefficient of negative 0.9656. That's close to -1, so we have a strong fit, meaning our model is good for making predictions. Retyping my model using function notation, again, will just allow me to evaluate that linear model for a specific value. In this case, let's consider predicting for n equals 22. So we're going to evaluate f of 22. And we get 8.5027. If we're plugging in 22, this is a case of extrapolation, because 22 is larger than any of the values that we had for school enrollments in our original data set. But we're not extrapolating very far beyond the original data. So while extrapolation does get us into this realm of potentially less reliable results, the closer we are to that original data, it's more likely the model still fits. So this number we're going to assume is fairly reliable. And then we want to interpret those values that we came up with in part C. So this means that we would expect a region with, we plugged in 22, but keep in mind that converts to 22,000. We would expect a region with 22,000 school enrollments to have 8.5027, but if we multiply that by 1,000, and then we would intuitively round, since we're talking about a number of people, we would expect that region to have 8,503 people living under the poverty level. So we adjusted those values into the thousands. We round intuitively, since we're talking about people, we can't have a part of a person. And then again, recognize that what we're doing is estimating. We're predicting a future unknown value. We're extrapolating because the value that we're using is outside our original data, but it's still pretty close. So there's a good chance this number is pretty reliable. And then the way to tell for sure would be to find a region with that many school enrollments and see how well that stacks up to our prediction.